Hi, it's already week 9 that we are in, and I'm kind of excited for today's uh, the things I'm going to cover today. I'm going to start with order notation, and then I will be talking about the ways of counting and counting principles in general. Um, so yeah, let's get started. So we're talking about order notation right now, right? So before that, let me define what an algorithm is. So an algorithm is a fully specified computational method for producing outputs from inputs. If you're given an input, any algorithm will eventually stop computing and deliver an answer and give the same input on some subsequent occasion. It will produce the same output. That is the relation between input and output of an algorithm is a function. This relation exactly, uniquely defined and defined for all values in the domain. Let's go over this definition again. So an algorithm is basically just you're given an input and you want an output, and there are some steps that you have defined in that algorithm to get the output. And any number of times you're given that particular input, no matter what time it will always give you back the same output, right? So that is the relation between input and output, and it's called a function. So it's basically a function that you write an algorithm of, right? You must have heard another word called pseudocode right, or code itself. So algorithm is a formal way of writing the code, but in mathematical form, and the code is that in a way that the computer understands, right? So again, algorithm is just a fully specified computational method that you use. What's the simplest algorithm that I could think of? Well, if you're given an array of numbers, let's say 1 to 10, and you want to find the number 6, so how do you do it? You start from the first indexed array. So like an array would be of the form um, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 numbers, right? It could be of any order, but what I want to see is I want to find the number 7, right? So one way it's called a simple search, that you start from the first element, you check if that element, that is array I start with I, right? I equal to 1. So is 1 equal to the number I want to find? The number I want to find is 7. It's not. I keep on going, right? So that's a form of an algorithm. Like it's called simple search. That you start from 1, you go to, if you don't get it, you go to the next element, 2, 3, 4, 5, 6, and you get it at 7, right? So this is one form of an algorithm. It's called a simple search, where you're given an input, you want an output, and you just want to see that if it exists or not. If that element is the number you're searching for, then it returns a true value that yeah, it is there in the array, right? There are different ways to solve this particular problem of searching an element in the array. You can learn about them maybe in the algorithms courses, but there's simple search, binary search, and a lot of other things, right? So yeah, that's the simplest algorithm you can think of: inputs and outputs, and there are computational steps that are written down for you to get it done with. All right. Time is one factor that may limit the usefulness of an algorithm. Here what you see is that I wanted to search for 7, right? I went from 1, 2, 3, 4, 5, 6, 7. If I was looking for the number 10, then I'll have to ask this question, that if the array I is equal to the number I'm searching for 10 times, right? So that's not an efficient way. So time is one factor that may limit the usefulness of an algorithm. Another potential constraint is the amount of memory it uses. For us, memory is of secondary importance, since an algorithm can only make use of memory that it takes the time to access. Therefore, if the units are chosen appropriately, any algorithm uses at least as much time as the memory, and memory is often considered to as space. So we usually define the order of a function or the complexities in two ways. It's called time complexity and space complexity. Space complexity is just the amount of memory that you consume while you're solving the particular question or particular algorithm. And the time complexity is the number of questions you ask and the computational time that it takes. For the one that we're looking for, the simple search, this was just one question, so it should just take 1 unit of time, right? And it asks that question n times, or the order of n. What did I mean by order of n? N is basically the number of elements in it, so that's 10. So I can ask it 10 times. I might have to ask it 10 times. What if I am looking for the number 3? I'll just have to ask it 3 times, right? So there comes the concept of worst case scenario and average case scenario. So worst case analysis makes sense because if we know the size of the input, the result of an analysis allows us to give ironclad guarantees about how long we might have to wait for a computation to end. So we might have to wait. So it could have been 10 units of time, or it could have been just 1 unit of time. The worst case scenario is 10 units of time, and that's why we call it the order of n, right? Next thing was average case. So that was the worst case scenario, right? I mean, it's the last element. What do you do next? If we expect to run the algorithm on many different inputs and prefer an approach that is faster overall, though it may be slower for some individual inputs, an average case analysis requires knowing something about what the average case of the possible inputs would actually be, and therefore tends to be trickier and less widely acceptable than the worst case analysis. Now, I'll just give you an intuition about how the binary search algorithm works. You divide it into two parts, divide the array into two parts. It's 1, 2, 3, 4, 5 and 6, 7, 8, 9, 10. You check at this element, at number 6, if the number you are finding n is greater than the current element. If it is greater than the current element, then you don't even need to look at 1, 2, 3, 4, 5 anymore, because you know that 7 is greater than 6. Now your whole, the whole focus needs to be on this array, and so you keep on breaking it down until you have it, right? So the number of questions you might have to ask would be lower. So the number of complexity, the amount of time complexity will actually decrease. Alright, so we'll go through that. So that's what an order of function is. So the first one that we saw is the constant function, where fn is equal to c, linear function is an plus b, quadratic is an square plus bc plus c, bn plus c. Polynomial function would be anything of the order of k, and exponential would be e to the power something. So just keep these functions in mind, and we'll go through that. Maybe you'll go through them in the exercises. Monotonic functions are functions where if for any m that is greater than n, then fm is always greater than fn. So you'll just look at it as only increasing or only decreasing. So you call them as monotonically increasing or monotonically decreasing. Their behavior would not waver, that once it is increasing in a period, then it decreases in a period. That wouldn't be the case. Okay, so that was the what an algorithm is, and let's look at limits for now, so that we can define orders in a better way. So very basic concepts of limits. If you have a constant c, then whatever the value of n be, it wouldn't affect the limit n tends to infinity for c, and which would always be c. But now if you have limit n tends to infinity for n, then the value of n would tend to infinity, and hence the limit would be infinity. And similarly for 1 by n, so 1 by n is 1 by infinity, so that would be 0, right? So if n tends to infinity, 1 by n would give 0. These are very basic concepts of limits. We're given a function, we're given two functions, and we define a third function, fn plus gn, and we then the limit n tends to infinity can be written as limit n tends to infinity for fn plus limit n tends to infinity of gn, right? Now something to note here is that there is something called undefined forms. Now there could be any of these ones that you see, that 0 raised to 0, or infinity raised to 0, infinity minus infinity, 0 times infinity, infinity times 0. So there are specific methods that you use to solve some of them. But generally speaking, if you have this function and none of the two functions, the constituent functions, are of any of the indeterminate forms, then you can try to solve them individually and get the answer for fn plus gn limit n tends to infinity, right? Okay, so there is one more rule that you need to be aware of, that's called the L'Hospital. What it says is that if you have a function of the type of 0 by 0 or infinity by infinity, then limit n tends to infinity fn by gn can also be solved as limit n tends to infinity f dash n, that's the first derivative of fn, f for n, and then the first derivative of g for n. So that's limit n tends to infinity f dash n upon g dash n, right? But for this, f dash n and g dash n should exist at point n, and hence, and should not be 0. The denominator should never be 0, obviously, right? So that's the L'Hospital. Let's do a question. For a very basic question, you're given the question that limit x tends to find the value of 8 minus 3x plus 12x squared. So now a limit is always defined in the neighborhood of this particular value, that is 2, right? So you're given 2 plus h, 2 minus h, right? I could write this. So this is one basic form. Just put in the values of 2 here, you'll get 50, right? Let's do the same thing again, but with some difference. What I say that it's in the neighborhood of 2, right? So it's going to be 2 plus h. Now that will be of the case 3 plus 6. I'll subtract this part. It will be 6 minus 3h plus 12 times 4 plus 12 times 4h plus 12 times h square. Now you need to understand that h would tend to 0 when I say that h is in the neighborhood of 2, right? So that would give us 8 minus 6 plus 48. Okay, I think I'm writing it in that form. Is equal to 8 minus 6 plus 48 minus 3h plus 48h plus 12h square. Now the whole thing would be 0 because h tends to 0, and this would just give us the value of 50. Okay, so that's how you calculate find the limit for x tends to 2. Just put in the values of 2 and you'll get the answer if it's not in the indeterminate form. Now a good question is, what is the limit x tends to infinity 2x plus 7 3x square minus 5? You put in the value of infinity, you'll have the form of infinity by infinity, that is an indeterminate form. What do you do next? Let's use the L'Hopital rule. What did it state? Where did it go? Yeah, if you're given it of the form 0 by 0 or infinity by infinity, just find the derivative of both the functions, of both the numerator and the denominator. So you have 2x plus 7 and 3x square minus 5. That will be 2, find the first derivative of both of them. You'll have 2 plus 0 and 3 times 2 times x minus 0. So that's 2 by 6x, that is 1 by 3x. If you put infinity in the denominator, you'll have it as 0, right? Because 3 times infinity is infinity and 1 by infinity is 0, right? So the limit for 2x plus 7 upon 3x square minus 5 and x tends to infinity is actually 0. Now we come back to the discussion we were having about the algorithms, where now we are defining what asymptotically equivalent functions are. So that just means that we are talking about the rate of the growth of the function fn and gn. Now if when limit n tends to infinity both of them are same, then they're called asymptotically equivalent. Now when we talk asymptotically, it just means that we are talking about the function in itself, the function in entirety, rather than a value of the function at a particular point. So we are saying that for the entirety of this function fn and gn, they would grow equally. So that's asymptotically equivalent. That's fn upon gn for limit n tends to infinity is 1. Something that you need to know also is the factorial n can be written in this format. You will have this in the textbook if you have a small reading, where n factorial can be written as the product of all i's from 1 to n. I is equivalent to square root of 2 pi n times n upon epsilon raised to n. You'll have a discussion in the textbook for this as well. Now comes the big question, defining the rate of the growth or the growth of the function. The first one is big O. You might have seen something of the form of O of n or O of n square somewhere. What does this mean? So n is just a function on n square is also another function on n. So this specifies an upper bound on the runtime of the particular function, wherein it denotes the functions that do not grow faster than g of n. And we define that group of functions as O of g of n. Let's take two functions, that f of n is equal to n and f of n is equal to n square. When you take different values of n, let's take 1, 2, 3, 4 and 5. The values of n would be 1, 4, 9, 16 and 25. Sorry, that's fn squared. and the value of fn would be just be the 1 2 3 4 5, so it keeps on increasing. But f of n of sorry g of n would be increasing greater than f of n, so we can say that f of n would not grow faster than g of n for any value of n. So that's why we can say that f of n big O g of n, that is n is the big O of n squared, right? So that way you can say that like it's just a group of functions that will fit in O of n. Now this equal to is actually equivalent to like it is in the set of those functions that do not grow faster than n square, right? And another use case is another thing to note is that if there is a degree n raised to k, there's a like this is the degree of a polynomial. There's another polynomial of the form n raised to k, n raised to k and n raised to m, right? This is the first polynomial and this is the second polynomial, and these are the highest degree terms. So if m is greater than k, then the first function, that is n raised to k, will always be the in the set of the functions that do not grow faster than that. So if the degree of a polynomial is greater, then the rate of its growth will also be greater. So I'm just saying that these are two functions, two polynomials, right? N raised to k and n raised to m. And if m is greater than k, then nk can be written as big O of n raised to m. Similarly, we had big O right here. So that was about that do not grow faster than m, than gn. Similarly, we have something that say that it grows faster than g of n, right? So that is, we define that group of functions as big omega of g of n, right? So in this case, what we had was that f of n was big O of g of n, but here if I had to write it in terms of omega, then g of n would have been equal to big omega of f of n, because it does grow faster than g of n, right? Now when we talk about the growth of a function, we had omega and big O and big omega. So both of them had greater than equal to, right? What if they both are, what if the rate of growth is same? So they are called symmetric functions, right? So this is strict, they're not strictly increasing or strictly decreasing. They're equal and increasing, equal and decreasing, right? So what if a function is strictly increasing? That will be little o and little omega for the ones that do not grow, that actually grow faster than g of n, right? The only difference between omega and little omega is that this is strictly greater than and big O is strictly less than, okay? This is a good question to solve. What is the asymptotic runtime for each of the following algorithms for computing k raised to n? Now you have to find k raised to n, where k is an integer and n is greater than 1 is a power of 2. Okay, so you set x is equal to 1 in both of them, set I equal to 1 in both of them. Now here is the good case. While I is less than n, x is equal to k times x, and I is equal to I plus 1. Now here you have I is less than n, x is equal to x square, I is equal to 2i. Here you're adding I each time, right? How many times does this function work? I goes from 1 to n and it keeps on adding plus 1 plus 1 plus 1. So this runs for n times. Do you see why it runs for n times? Because I equal to 1 in the first case, I increased by 1, so I equal to 2 now, then it's again less than n, so you'll have 3, 4, 5, 6 for n times. While this function, if the initial value is 1, 1 is less than n, but now it becomes 2, next time it becomes 4, then 8, then 16, right? So it will be of the form of log n times. You'll understand why it's log n times, but the values that are taken in, just type the values that it will take in. This is about the first algorithm, takes in 1, 2, 3, 4, 5, 6, 7, 8, right? So 8 times this function will be run, while algorithm 2 will run for 1, 2, 4 and 8. So it just runs for 4 times, right? and this one would have run for 8 times. You see how it is different. So that's how you would calculate the asymptotic runtime and for any general n. Next question is, let fn and gn be functions from n, the natural number to real numbers. Prove or disprove the following statements. Fn is big O of gn implies gn is a big O of f of n. Oh, does it mean that? I think that's a homework question. Alright, fn is omega g of n if and only if g of n is equal to little o of f of n. So that is, if fn is strictly lower than g of n, sorry, if fn is strictly greater than g of n, if and only if gn is equal to, if gn is strictly decreasing when compared to f of n, right? How would you do that? Just make sure when you're solving this that the first question is implies. So if you prove this, sorry, if you assume this and you prove g of n is equal to big O of f of n, that will be okay. But since the part B is an if and only if statement, just make sure you prove it both ways. Assume this part, prove this part, and the second case would be assume this part and prove this part. You have to go both ways to prove or disprove. Disproving would be okay, just prove one part is false, but to prove it, it has to go both ways. Which of the following holds true, prove or disprove in each case? I'll just solve one of these questions. That you are given 64n plus 2 raised to 5 is equal to little o of 3 raised to n raised to 3 times n raised to 4. Now what does little o mean? Just take 10 seconds and try to answer that question. What little o means? When I said big O of g of n, that meant that O, like the big O of g of n, would have all the functions that are slower than g of n, right? So can I say that 64n plus 2 raised to 5 is strictly slower than 3 raised to n raised to 4? I think it is, because this will increase by the power of, it is n raised to 1, this is n raised to 4. Look back to our example of n raised to m and n raised to k, and this is n raised to 1 and this is n raised to 4. So this is greater, so the rate of change would be greater for 3 times n raised to 4 than 64n plus 2 raised to 5, right? All right, and then you can do the next questions. If you have any queries, please feel free to reach out to me. Prove that the asymptotic equivalence of functions is an equivalence relation. Now to prove that a function or any relation is an equivalence relation, we just need to show 3 properties: reflexive, symmetric, transitive. So if you're given a function fn and you're given another function gn, and you know that fn, so let's do this. If you're given a function fn, the reflexive property would have to be that fn is big O of fn, and f of n would have to be, can you add that? Sorry for that, omega of f of n. You need to prove that for this. I'm assuming that it is not strictly increasing and decreasing, but you can also use that to, you can also prove that as well, which would not be the case, because for strictly increasing, okay, anyways, I'll let you find that out, but this is how you do it. For symmetric, you would have to take fn and gn. You would assume f of n is is an element of big O of g of n, and the other way around, to show that it is true for both of them, and hence for the transitivity. And this is the end for this week's section. For order of functions, what we learned was, we started with discussing what algorithms are. We went to the different kinds of order of functions. We discussed what is, let me just go over it. Algorithms and worst case scenario, average case scenario, types of order functions, monotonic functions, limits, how do you solve limits, like the L-Hospital rule, and couple of questions on that. What is asymptotically equivalent? Growth of functions, big O, big omega, little o, little omega, and we did a couple of questions on finding the asymptotic runtime, and that's it for this section, right? And then I'll be posting another video for the counting discussion as well, different principles for counting. Thank you.